Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The year 1964 marks a pivotal moment in the history of optical communications, witnessed by the publication of dielectric fiber surface waveguides for optical frequencies by Charles Kuen. This manuscript, a beacon illuminating the path towards modern fiber optics, warrants rigorous examination. The following essay undertakes a systematic evaluation of the claims presented within Kwen's seminal work, dissecting its arguments, assessing its methodology, and contextualizing its significance within the evolving landscape of telecommunications. Our objective centers on a critical assessment of the paper's internal consistency and the validity of its assertions, offering insights into its enduring impact on science and engineering. Section 1: Introduction of Optical Waveguides and Potential. The introduction of dielectric fiber surface waveguides for optical frequencies establishes the fundamental premise, asserting the feasibility of utilizing dielectric fibers as waveguides for optical frequencies. Kwen posits that these fibers, composed of transparent material, offer a promising avenue for transmitting data over long distances, an improvement over existing communication methods. The work emphasizes a potential superiority of optical frequencies compared to radio frequencies for signal transmission, citing the increased bandwidth capacity achievable in the optical spectrum. This initial proposition requires careful consideration, as it sets the stage for the subsequent analysis of practical limitations and theoretical considerations. Kwen boldly states the potential for low-loss optical waveguides. This is a powerful initial claim which warrants the subsequent in-depth exploration of material purity and waveguide geometry. Section 2: Material Selection and Attenuation Considerations. The second section delves into the critical aspect of material selection, focusing keenly on reducing signal attenuation within the dielectric fibers. Kwen identifies existing glass compositions, typically employed in conventional optics, as presenting unacceptably high levels of optical loss at the telecommunication wavelengths. He correctly attributes this attenuation primarily to the presence of impurities within the glass matrix. Kwen proposes that reducing these impurities to extremely low levels is essential to achieve practical long-distance optical transmission. The work advocates for the exploration of novel materials and purification techniques. The exploration of such techniques is presented as paramount to realizing the theoretical potential of optical fiber communications. The claim that impurity reduction is a primary path demands careful inspection. Section 3: Waveguide Structure and Mode Propagation. This section investigates the structure of the proposed dielectric fiber waveguide and analyzes the behavior of light propagating within it. Kwen elucidates the concept of total internal reflection. This reflection confines light within the fiber core, guiding it along the fiber's extent. This analysis explores the different modes of light propagation, carefully describing how the fiber's dimensions and refractive index profile influence the characteristics of these modes. Kwen accurately describes the relationship between fiber diameter, wavelength, and the number of propagating modes. Smaller diameter fibers support fewer modes, potentially leading to reduced signal dispersion. This section presents a very strong argument for the importance of careful waveguide design in optimizing signal transmission characteristics. The investigation of mode propagation is essential to understanding the limitations imposed by multimode dispersion. Section 4: Theoretical Loss Mechanisms and Attenuation Calculations. The fourth section presents a detailed examination of theoretical loss mechanisms affecting optical signal propagation within the dielectric fibers. Kwen meticulously analyzes absorption, scattering, and waveguide imperfections as sources of signal attenuation. Absorption arises from the interaction of light with the material's atoms and molecules, converting optical energy into heat. Scattering, caused by inhomogeneities within the material, redirects light, diminishing the intensity of the forward propagating signal waveguide imperfections, such as variations in fiber diameter or refractive index, similarly contribute to signal loss. Kau provides quantitative estimates of the attenuation caused by each of these mechanisms based on available data and theoretical models. These calculations are crucial to determining the feasibility of long-distance optical communication. The meticulous estimation and calculation of each attenuation mechanism were examined, providing a basis for comparison with experimental results. Section 5 Assessment of potential low-loss materials. Kau assesses the suitability of various materials for constructing low-loss optical fibers. The work explores the properties of fused silica, a high-purity form of glass. Fused silica possesses a relatively low refractive index and exhibits minimal absorption at certain optical wavelengths. Kau recognizes the potential of fused silica as a promising candidate material, but emphasizes the need for further purification to eliminate residual impurities. The section also considers alternative materials, such as single crystal materials, which may offer superior optical properties. However, the practical challenges associated with manufacturing long, uniform single crystal fibers at the time are duly acknowledged. This section provides a balanced evaluation of potential materials, focusing on their optical properties and manufacturing feasibility. This evaluation informs the subsequent exploration of methods for reducing losses in fused silica fibers. Section 6 Impurity Reduction and Fabrication Techniques. This section focuses on the critical problem of impurity reduction and explores potential fabrication techniques for manufacturing low-loss dielectric fibers. Kau emphasizes the importance of employing high-purity starting materials and utilizing carefully controlled fabrication processes to minimize contamination. The work discusses various purification methods, such as vapor phase deposition, which allows for the creation of highly pure silica glass. Kau also considers the fabrication of fibers using drawing techniques, where a form of pure glass is heated and drawn into a thin fiber. The success of these techniques depends on maintaining a pristine environment and preventing the introduction of impurities during the drawing process. This section outlines several avenues for achieving low-loss fibers through careful material selection and fabrication. This careful selection and fabrication is examined and the potential limitations are explored. Section 7 Waveguide Geometry and Mode Control. The influence of waveguide geometry on mode propagation and signal dispersion is investigated. Kau discusses the advantages of single-mode fibers, which support the propagation of only one mode of light. Single-mode fibers are less susceptible to modal dispersion, a phenomenon where different modes travel at different speeds, leading to signal broadening. Kau notes that reducing the fiber core diameter is essential to achieve single-mode operation at optical wavelengths. The work also considers the impact of the refractive index profile on mode confinement and signal transmission characteristics. Precisely controlling the refractive index profile allows optimization of the fiber's performance on minimizing losses and dispersion. This section shows how waveguide geometry can be engineered to improve signal quality and transmission distance. The engineering of waveguide geometry to improve signal quality is essential for maximizing transmission length. Section 8 Dispersion Effects and Bandwidth Limitations. This section delves into the effects of dispersion on signal transmission bandwidth. Kau identifies two primary types of dispersion: modal dispersion, which occurs in multimode fibers, and chromatic dispersion, which arises from the wavelength dependence of the refractive index. Modal dispersion can be minimized by using single-mode fibers. Chromatic dispersion presents a more complex challenge, requiring careful material selection and waveguide design. Kau discusses the use of dispersion compensating techniques, such as employing fibers with tailored refractive index profiles to counteract the effects of chromatic dispersion. Minimizing dispersion is essential to achieving high data transmission rates over long distances. The careful mitigation of dispersion permits the attainment of high data transmission rates. Section 9 Connectors and Splices. Practical considerations. Kau acknowledges the practical challenges associated with connecting and splicing optical fibers. Low-loss connections are essential to maintain signal integrity over long distances. The work discusses various connector designs and splicing techniques, emphasizing the importance of precise alignment and minimal insertion loss. Fiber connectors must provide secure and reliable connections, while splicers must create seamless joints between fibers. Achieving low-loss connections and splices requires careful attention to detail and specialized equipment. Kuen recognizes that the development of robust and practical connection technologies is crucial to the widespread adoption of optical fiber communication systems. The development of robust and practical connection technologies will enable the proliferation of optical fiber communication systems. Section 10. Proposed communication system and potential applications. This section outlines a conceptual optical fiber communication system and discusses its potential applications. Kuen envisions a system consisting of a light source, an optical fiber transmission line, and a photodetector. Light-emitting diodes or lasers can serve as light sources, while photodiodes or avalanche photodiodes can detect the optical signal at the receiving end. The work highlights the potential of optical fiber communication for a wide range of applications, including telecommunications, data transmission, and sensing. Kuen emphasizes the ability of optical fibers to transmit large amounts of data over long distances with minimal signal loss or interference. This section provides a glimpse into the future of optical communication and its transformative potential. The transformative potential of optical communication will revolutionize fields reliant on data transmission. Section 11. Economic considerations and future outlook. Kuen addresses the economic considerations associated with optical fiber communication systems. The initial cost of developing and deploying optical fiber infrastructure is significant, but Kuen argues that the long-term benefits outweigh the initial investment. Optical fibers offer a higher bandwidth capacity, lower signal attenuation, and greater immunity to interference compared to traditional copper cables. These advantages translate into lower operating costs and improved system performance. Kuen expresses optimism about the future of optical fiber communication, predicting that it will eventually replace copper cables as the dominant transmission medium. This section presents a compelling economic case for the adoption of optical fiber technology. The economic adoption of optical fiber technology is the driving force behind the widespread use of fiber optic cables. Section 12. Discussion of contemporary critiques and alternative approaches. At the time of publication, Kuen's proposals faced skepticism from some members of the scientific community. Some questioned the feasibility of achieving the extremely low levels of optical loss required for practical long-distance communication. Alternative approaches, such as microwave waveguides, were also being explored. Kuen acknowledges these critiques but maintains the potential superiority of optical fiber communication if the challenges of attenuation and dispersion can be overcome. The work emphasizes the need for continued research and development to realize the full potential of optical fibers. The pursuit of research and development efforts, the key to unleashing the full potential of optical fibers. Section 13. Evaluation of Kuen's loss estimates and material purity. Kuen's paper makes bold claims regarding achievable transmission losses within optical fibers, specifically suggesting that losses could be reduced to levels far below those observed in existing optical materials. A critical evaluation suggests that these initial estimates, while optimistic and necessary for galvanizing research efforts, were based on theoretical projections rather than empirical data. The actual realization of these low-loss fibers proved considerably more challenging than initially anticipated, requiring significant advancements in material purification techniques. The early focus on fused silica, while ultimately successful, also initially overlooked other potential candidate materials that might have offered unique advantages. The claim that initial estimates were optimistic is carefully considered in comparison to the significant advancements required to achieve these theoretical projections. Section 14 Analysis of waveguide imperfection effects on signal integrity. While Kuen acknowledged the impact of waveguide imperfections on signal attenuation, the initial treatment of these imperfections lacked the nuanced understanding that would emerge in subsequent years. The paper primarily focused on macroscopic variations in fiber diameter and refractive index. The detrimental effects of microscopic defects and surface roughness on light scattering received less emphasis. Additionally, the complex interplay between fiber drawing processes and the creation of these imperfections was not fully appreciated at the time. Later research revealed that extremely fine-scale control over the fiber drawing process is essential to minimize scattering losses caused by these subtle imperfections. The complexity lies in the interplay between fiber drawing processes and minimizing scattering losses. Section 15 Assessment of single-mode fiber fabrication challenges. Kuen correctly identified the advantages of single-mode fibers for minimizing modal dispersion, but the practical challenges of fabricating these fibers with sufficient precision posed a significant hurdle. Achieving the required core diameters and refractive index control demanded unprecedented levels of manufacturing precision. Furthermore, maintaining these precise parameters over long fiber lengths presented a formidable engineering challenge. Early attempts to fabricate single-mode fibers often resulted in unacceptable levels of attenuation due to imperfections in the core-cladding interface. It was the development of advanced fiber drawing techniques and improved control over the refractive index profile that eventually enabled the widespread deployment of single-mode fiber optic communication systems. The development of advanced fiber drawing techniques is essential to producing single-mode fibers. Section 16 Evaluating dispersion compensation techniques. Kuen's initial discussion of dispersion compensation techniques provided a conceptual overview of the problem, but lacked the depth of understanding that would develop with subsequent research. The limitations of simple dispersion compensation schemes, such as using fibers with fixed refractive index profiles, became apparent as data transmission rates increased. Higher data rates demanded more sophisticated dispersion management strategies, including the use of dispersion compensating fibers, chirped fiber Bragg gratings, and electronic dispersion equalization. These advanced techniques allow for precise control over the accumulated dispersion experienced by the optical signal, enabling much longer transmission distances and higher data rates. The precision afforded by these advanced techniques has enabled long-distance transmissions. Section 17 Scrutiny of connector and splicing loss minimization. Kuen recognized the importance of minimizing losses associated with connectors and splices, but the early solutions available were relatively crude compared to modern technologies. Initial connector designs often relied on mechanical alignment, which proved susceptible to variations in temperature and vibration. Splicing techniques involved manually aligning and fusing the fiber ends, a process that required considerable skill and precision. Modern connectors utilize advanced alignment mechanisms and precision ferrules to minimize insertion, loss, and back reflection. Fusion splicing techniques have also advanced significantly, incorporating automated alignment and arc fusion control to create highly reliable and low-loss joints. The advances in fusion splicing techniques permits the creation of highly reliable joints. Section 18 The evolution of light sources through LEDs to lasers. Kuen's initial suggestion of using light-emitting diodes as light sources for optical fiber communication systems proved limiting due to their relatively low power output and broad spectral width. Lasers, with their higher power, narrower spectral width, and superior coherence properties, rapidly emerged as the preferred light source. The development of semiconductor lasers, such as gallium arsenide lasers and indium phosphide lasers, revolutionized optical communication. These lasers provide the high power and narrow spectral width required for long-distance, high bandwidth transmission. The development of semiconductor lasers revolutionized high bandwidth transmission. Section 19 Detector technology improvements. Photodiodes advance. The evolution of photodetector technology also played a crucial role in the advancement of optical fiber communication. Photodetectors, such as germanium photodiodes, suffered from relatively high levels of noise and limited sensitivity. The development of silicon photodiodes and avalanche photodiodes (APDs) greatly improved detector performance. APT, with their internal gain mechanism, offer significantly enhanced sensitivity, allowing for the detection of weaker optical signals. These improvements in detector technology enabled longer transmission distances and improved system performance. Improvements in detector sensitivity enabled longer transmission distances. Section 20 Contemporary revisions of Kwen's system. Model modernization. Kwen's initial system model, while visionary, required significant revisions to accommodate the advancements in optical fiber technology. The introduction of wavelength division multiplexing WDDM allowed for the transmission of multiple optical signals over a single fiber, dramatically increasing the overall bandwidth capacity. Coherent optical communication techniques, which utilize advanced modulation formats and digital signal processing, further enhance system performance and spectral efficiency. Modern optical fiber communication systems incorporate sophisticated network management and control functionalities, ensuring reliable and efficient data transmission. The introduction of wavelength division multiplexing dramatically increased bandwidth. Section 21. The enduring significance of foundation laid, despite the inevitable advancements and revisions that have occurred since its publication. Dielectric fiber surface waveguides for optical frequencies remains a landmark achievement. Kwen's paper provided a crucial conceptual framework for the development of optical fiber communication. It articulated the fundamental principles, identified the key challenges, and outlined a path towards realizing the full potential of this transformative technology. Kwen's work served as a catalyst for intensive research and development efforts worldwide, leading to the widespread deployment of optical fiber communication systems that underpin the modern Internet and global telecommunications infrastructure. The paper's conceptual framework catalyzed research and development worldwide. Section 22 Conclusion. The legacy of Kwen's vision. In conclusion, the claims presented in Dielectric fiber surface waveguides for optical frequencies by Charles Kuen were, on balance, both visionary and foundational. While some of the initial estimates regarding achievable losses and the ease of fabrication proved optimistic, the central thesis that optical fibers could serve as a viable medium for long-distance communication at optical frequencies proved remarkably prescient. The paper identified the key challenges: attenuation, dispersion, and connector losses that needed to be addressed, and it outlined a plausible path towards overcoming these hurdles. The subsequent decades of research and development, spurred by Kwen's work, have transformed the world, enabling the global information society we experience today. Kwen's meticulous analyses of waveguide geometry and material constraints provided a roadmap for future innovations. His earlier insights into dispersion effects also foreshadowed challenges that would demand substantial technological solutions. The enduring legacy of dielectric fiber surface waveguides for optical frequencies lies not only in its technical content, but also in its visionary foresight and its ability to inspire a generation of scientists and engineers to pursue the seemingly impossible. The legacy of the paper inspires scientists and engineers to pursue the seemingly impossible.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.